For centuries, light was modeled as a simple, straight ray. But in 1678, Christian Huygens proposed a different physical mechanism. Light actually travels as a propagating transverse wave. Think of dropping a pebble into a still pond. The expanding ripples you see are wavefronts. A wavefront is simply a surface where every point on that curve is vibrating in the exact same state, or a constant phase. If we draw a straight line straight outward from the source, we get our traditional light ray showing the direction of travel. Look at the angle where that ray intersects the wavefront. It is always exactly perpendicular. This consistent right angle allows us to determine the trajectory of light by simply observing the orientation of its wavefront. Looking at these three diagram boxes, the light source's shape dictates the wavefront's geometry. Take a light bulb. Acting as a point source, it radiates energy outward, creating concentric spheres. But forcing light through a slit changes the geometry. This linear source creates concentric cylinders. So what happens to that expanding curvature if the light source is millions of miles away, like the sun? By the time those waves travel the vast distance to reach Earth, the curves have completely flattened out. We model these as plane wavefronts, drawn as flat parallel lines. As the distance from the source grows, the wavefront's curvature gradually vanishes, transforming a radial expansion into a set of parallel planes. To explain how these waves travel, Huygens proposed every single point on a wavefront acts as a new source. These points sprout forward-moving secondary wavelets, expanding at the speed of light. Tracing a tangent surface connecting their outer edges reveals the new wavefront's position. This orange concept booster notes that when these wavelets overlap and interact with each other, they produce the observable patterns of interference and diffraction. This behavior confirms light acts as a wave, yet the wave model alone couldn't explain every interaction. Arthur Compton's work, shown here, demonstrated that light also behaves as discrete particles, creating a dual nature that physics must account for. Light carries both identities. However, to trace how a beam propagates and bends through physical space, Huygens' macroscopic wave model provides the necessary geometry. This numerical example section shows how we apply these rules to find the speed of light in a new medium. First, extract your known variables, the starting speed, c, and the refractive index, n. Then substitute them into the velocity equation, v equals c divided by n. Dividing 2.0 times 10 to the 8th by the index of 1.50 gives a slower speed of 1.33 times 10 to the 8th meters per second. In the second example for frequency, watch out for a common error. The starting wavelength is in nanometers. You must convert that 500 into 500 times 10 to the negative 9th meters before substituting, or the final frequency will be incorrect. Let's review the core rules shown in this key points box. Wavefronts and rays are always perpendicular. Wavelength spacing is uniform in a single medium, and the medium's density dictates the final speed. By combining the geometric properties of the wavefront with these specific velocity and frequency formulas, we can map the physical behavior of light through any medium.